Okay, people, I think everybody's seen a lever. Now, a lever is composed of a fulcrum, which is the triangle, and that's a pivotal point. And here we have the weight, which is Newton's apple.
And the lever part itself right here.
Right, and if you go ahead and push on that end,
that's quite easy to push.
Pretty easy. One of the reasons you use a lever is to get a mechanical advantage so that you don't have to push as hard on that side to lift the apple. The reason that works is because the apple is closer to the fulcrum than you are. That gives you a mechanical advantage. Now there's another way to use a lever, and if you'll just lift the board up, I'll slide the fulcrum down to here. Okay, now try to lift it.
Ooh. Much harder. I can get it up there, but it's much harder to
because the apple is farther away from the fulcrum than you are, so it's very hard to lift.
Why would I want to use a lever to make something harder to lift?
You get something out of this, and that's velocity. If you notice, when you push down on that, you don't have to go very far to get the apple to move a very long distance.
You're right.
You're going down slower than the apple is coming up, so you gain in velocity.
Now, does that mean that this is how the body uses levers?
Well, no, this isn't exactly how the body uses levers, but it's similar. If you'll come up here, you remember I said that muscles can't push, they can only pull.
So they couldn't push on that end.
No, but what they do is they would grab on in here and try to lift. And that's...
Oh, just like... Well, it's hard. It's very hard as pushing on the other end.
It's very hard. That's how most of the levers and muscles and bones acting as levers in the body work.
Well, how does it actually construct it in the body?
Well, I brought a friend with me.
Well, let's take a look. Oh,
Dad Ernest, yeah.
He's all muscled up here.
Let me show you how most of the lever systems in the body work. The fulcrum is the joint. Okay, in this case, his elbow. The force, which is you lifting up on that board, is where the muscle attaches to the bone, and the weight is the apple in his hand. Now, when this muscle contracts, it contracts a very short distance to get his hand to move a very long distance.
So that while this may only shorten up just a tiny bit right here at the joint, this muscle here, the arm is going up and down.
That's right.
So the secret is then you can then move your arms and your legs very easily. You may not be able to lift up heavy weights, but you become very agile, which we all need to be.
Oh yeah, very important for survival.
I see.
And one of the best examples of this is a pitcher pitching a baseball. And I have a tape of a pitcher now pitching.
Oh yeah, it's our friend Ron Guidry.
Yeah, it certainly is. Now what a pitcher is going to do is use not just one lever system in his body, but many of the joints in his body as a series of levers to get the maximum velocity. Now what Ron Guidry is going to do is stretch way back.
This is so he gets a long lever out of his
arm? Long lever
arm?
arm, exactly. And he's going to get the ball way back, and then he's going to first bring his hips forward. That's velocity. Bring his shoulders forward then. That's velocity. Then he's going to bring his arm forward. That adds even more velocity. And finally, he's going to flick his wrist, and that's going to be the last little piece of velocity. And all those lever systems working together make it possible for some pitchers to pitch over 100 miles an hour.
So that explains how, if you add up all the leverage systems in our body, it helps us to become more agile and move quicker. What about using our levers as a weightlifter?
No, we don't want to do this in series. We want to, if you want to get a mechanical advantage in strength, now you're going to try to use all of your muscles simultaneously. And that's what the weightlifter is doing.
I see. Well, I would, Jan, if we hadn't run out of time, I'd go up there and lift those weights.
Oh, I'm sure you would.
Thank you very much for coming.
You're welcome.
And on the strength of that explanation, I think we can muscle our way to the next part of the program.
More party trivia. Fascinating fact, number 136. Fish. When the going gets tough, the tough change sex. At least, that's true of the Red Sea anthias fish. If there's a shortage of eligible males around, the largest female will change sex so she'll have plenty of mates to choose from. The only catch is that once she's taken the plunge, there's no switching back.
Einstein's theory of relativity. It's one of the most famous and least understood concepts in all of science. yet we've received lots of mail asking us to explain it. It's a theory so complex, wouldn't it be great if we could put the question to the man himself? Let's meet our special guest. Welcome to Newton's Apple, Professor Einstein.
Ah, nice to meet you, Ida.
It's our privilege to have you here.
Thank you.
You know, when you first proposed the theory of relativity in 1905, it was one of the most revolutionary ideas since Isaac Newton, was it not?
Yeah. First of all, let me tell you an interesting story about Sir Isaac Newton, of the time that he was sitting under the apple tree when the apple fell out of the tree and hit him in the head. Immediately he said, gravity will always make the apple fall downward to earth. Then he went on to say that time, space, and motion are absolute. And of course, this is where we disagree.
This is where you disagree with him.
I must say so, Ira, I think he's the greatest scientist of all mankind, for he helped us step closer to understanding the mysteries of the universe.
Then where do you disagree with him?
Well, he says that objects travel in space in a straight line unless some other force acts upon them like gravity. But when I thought about it, I wondered if it wasn't the nature of space itself.
It's space itself.
Yeah, let's take a look.
All right. What have you got here? It looks like a table.
Aha, this is my universe. Fabric of space.
Okay.
Polyester, I think.
Okay.
And this is the moon.
All right.
Please roll it on the flat surface. Aha.
It goes in a straight line.
Exactly.
All right. That's not unusual.
Good. Now, let us see what happens when we take mass, Earth, and put it in the universe.
And I roll it. Look, it goes in a circle this time. It's almost like it's in orbit around there.
It is exactly, it is in orbit.
Wow. Why is that happening?
Because the fabric of space itself curves.
The fabric of space is curved. I don't see curved space around me here.
From our dimension. Take a look from another dimension, and then you will see the curve.
Look at that. Look at that. It really is amazing.
You see it orbit? As you could see that it is the mass itself that curves space.
And then it's the curvature that we really talk about as being the gravity. The curvature caused by the mass, which is curving space.
Exactly.
Now, is this what you call your theory of relativity?
This is part of the theory of relativity. There is still much more. Let's look at another part of time, space, and motion.
All right, let's go.
Ira, have you ever been riding on a train,
Yeah.
looking out of the window when another train moving in the same direction passes you by, and for that moment you think you are going backwards?
Yes, it's very confusing. You're not sure whether you're going backwards, the other train is going forward. What's happening there? Yes.
You see, because we are used to seeing the ground as our point of reference. But the minute we switch our point of reference to the train, that's when that happens.
Is there any way to measure from inside the train which train is moving in what direction?
No, because there's no absolute motion. And there's also no absolute time.
No absolute time. Now, this is going to be more difficult to understand, I think, the concept of no absolute time.
Let me show you what I tell my students and show them when I want to get them into the mood for this type of thinking.
All right.
Are you ready?
I'm ready. This is what you do.
What just happened?
You stepped your foot down twice.
Good. At different moments,
Different moments.
on the same spot.
Same spot.
This is not true.
Not true, you tricked me.
Yeah. You see, the room that we are in is located on Earth. When Earth is rotating on its axis, as it is also revolving around the sun, as the Earth and sun are moving through space. It is therefore wrong to say that the two stamps were on the same spot, because they were not while they were moving through space.
Now, I understand that there's no such thing as absolute time. I understand the point you're trying to make, but I don't quite clearly see it now. It's tough to see it around us,
Well,
you know?
to see it better, we have to imagine that we're traveling near the speed of light. We have to, if you would allow me to enter my imaginary world, when I thought about this for many, many years now, are you ready for this little trip?
What are you going to do here?
I'm going to put you on my imaginary train and take you to an imaginary experiment.
We're moving at the speed of light.
Near
Close to it.
near the speed of light.
All right, I'm ready to
Please
get on the
step in.
train.
Get in good, Ida, because we're going to be moving at great speeds. And when you move, look up at the sky, because there's a storm approaching. And look at the lightning flashes. And watch the lightning. There it is.
Oh, yes, I saw it. I saw it.
How'd you like that ride?
It was a very interesting ride.
Good. Now I would like you to tell me what you saw in my imagination.
Okay. What I saw in your imagination was I was riding on a train, I came to the storm, and I saw two flashes of lightning. I saw the lightning bolt in front of me flash first, and then the lightning bolt behind me flash second.
Good.
Isn't that what you saw here?
Nope.
You didn't see that standing here?
No, I saw 2 lightning bolts flashing at the same time.
Well, then how can that be?
The times that I measure here is different than the time that you measure moving in my train, because you and I are moving relative to each other. There is no absolute time.
I understand. Does that mean that I can't measure time in everyday life things? I can't see things like differences in time?
Well, it becomes more obvious for us to see if we were able to travel near the speed of light.
Oh, we have to be moving very quickly. Is there anything that's moving quick enough that we can measure the differences in time?
Well, clocks that we take out into space measure differently than the clock standing here on Earth, somewhat slower. When also the space astronauts, when they are in space, they age slower than the people here on Earth do. And you see, this is the concept of time and space that also led me to the realization of the connection between mass and energy.
Oh, your famous E equals mc squared formula.
Exactly. E is for energy, m is for mass, and c for the speed of light.
Professor, you got to tell me, how you come up with these interesting ideas?
I often ask myself, if I forgot, how would I make the universe? Acceleration, gravity, and
How many
inertia.
years does it take?
Oh, many, many years. And a lot of yo-yos.
Thank you very much, Professor Einstein, for making all of this relatively easy to understand. We'll be right back.